So in this video, we're going to look at one more strategy to help us with integration. That's by completing the square and by just using arc sine x, arc tan x, and arc secant x. So let's start off with a quick review. What are the derivatives of these three things? Arc sine x has a derivative of 1 over root 1 minus x squared. Arc tan x has a derivative of 1 over 1 plus x squared. And arc secant x has a derivative of 1 over the absolute value of x square root of x squared minus 1. So these are the things you should have memorized from the differentiation unit. These are the three we're going to be using. We're not going to be using the other ones like arc cos x or arc cosecant x because those are negative. It just makes it more difficult. So when we use integration, we're going to be sticking with these three basically. Now, we're going to get questions that sort of look something like this. And if you go further down the page, you can see when we get things like this, we can sort of match them up with one of these derivatives and use the integration in that way. So there are sort of opposite rules. There's the integration rules for these same things. So for the arc sine x, the equivalent integration rule is that the integral of 1 over the square root of a squared minus x squared dx is equal to arc sine x over a plus c. Sorry, that's supposed to say arc sine, a little bit messy there. So it looks very similar to the derivative of arc sine x. The only difference is this a value here. And we get that a value, just if you wanted to derive this, it's just by using a little bit of chain rule or substitution. But you can see that basically that a corresponds to whatever x is being divided by inside the sign. So if we can identify something that looks like this in an integral, we can use this pattern to come up with the integral. The equivalent one for tan x is 1 over a squared plus x squared. Again, we're going to use the a because that value isn't always 1. Sometimes it's usually something else. And the pattern here is 1 over a arc tan x over a plus c. So there you go, very similar to this one over here. And then we have an equivalent of arc secant, which you can maybe guess what it is. It's going to be 1 over x root x squared minus a squared. And that's going to give us, dx. Forgot about the dx equals 1 over a arc secant x over a plus c. So you notice this one, similar to the derivative of arc secant, has a restriction basically, the absolute value of x. That appears here in the integral as well, absolute value of x. And that just has to do with the restrictions of secant or arc secant. Okay, so basically, when we're doing integration and we try all our other methods and nothing works, we have something that's rational that might look something like this, this, or this. We can use that to sort of back substitute in order to come up with a derivative of that. So let's try this first question here. Before just running down to the question, does this match up with any of our patterns up here? It does, right? The one it closely resembles is this one here, the integral of arc secant x, right? That would give us arc secant x. So the key is we need to basically, for these ones, we need to identify what a is and what x is. So let me just zoom in there a little bit. So I'll try to leave that in the top corner, right? In our equation here, we have this x out in front, but we also have a 4x squared minus 9 in there. So the question is, what's sort of taking the place of the x squared and what's taking the place of the a squared? So the easy one is the 9, right? 9 is just 3 squared. So the a in this case would be 3, right? Because if you plugged in 3 into this pattern, we'd get the 9. What happens with the 4x squared? Well, I'm going to make a substitution because it doesn't just look like x squared, it looks like 4x squared. And in that substitution, the thing that makes sense is to look at it like this. 4x squared is equal to what squared? And it's equal to 2x all squared. So if I can put this 2x in the place of the x here, it's going to basically simplify everything for me. So I'm going to say u is equal to 2x, right? Because if we plugged in a and u into this thing, it would essentially look like this. So then I can essentially solve it using my u substitution method. So I can take the derivative of this, du by dx equals 2, and then I could solve for dx essentially. So dx is equal to, if we do a little bit of rearranging there, dx is going to be 1/2 du. And then I can make my substitutions into this equation, right? So I have the integral of dx is just 1/2 du. And that's going to be divided by x. And the simplification, we're going to make substitutions for x, right? So essentially u is 2x. So that means x is going to be u over 2, or 1/2 u, right? So let's make that substitution as well, 1/2 u. You'll see it's nice because those 1/2s cancel out. And then the thing inside the square root, well, remember, we substituted in u for 2x. So this ends up being u squared, right? U squared is 2x squared, which is 4x squared, minus 3 squared, because we made that substitution as well. Now we can simplify before applying our pattern. We can cross out those 1/2s. So we end up with essentially the integral of, I'm going to move that du off to the side as well. The integral of 1 over u square root of u squared minus 3 squared. Oops, 3 squared du. Now this looks very similar to this pattern that we have up here, right? We've essentially made it look like that. Instead of x's, we got u's, but it's exactly the same thing. So we just follow the pattern, right? So the integral of that is equal to this. So it's just going to be essentially 1 over a, and our a value we identified as 3, so it's 1 over 3. And then it's going to be, what is it? Arcsecant of the absolute value of, we don't have x anymore, we have u over a, which is 3 plus c, right? So see how that matches up perfectly with that pattern? Okay, now that we have that, we can back substitute for u, right? Because we want to have x in our final answer. Arcsecant of the absolute value of 2x over 3 plus c. And that's our answer. So see, we're essentially just on the lookout for patterns that look like these right here. And when we find them, we can make a few little substitutions and simplify them like that. Let's try the next question. This one looks sort of similar, a little bit different. Which one of the three do you think this one applies to? Well, if we look up here, it's got the square root, so we know it can't be the tan one, the arctan one. And it also doesn't have the x in front of the square root, so it can't be arcsecant. So it's got to be the arcsine one. So basically, we want to force this thing to look something like this somehow. Now, unfortunately, this one doesn't have anything that looks like this in the numerator. They've got sort of ones in the numerator for each of them. So we have to apply a little bit of algebra here to make it look more like this. So let's do that. We can do that just by using basic algebra, where if you have a fraction like this, we can break it up, we can split it up into two separate fractions. In this case, two separate integrals, right? So we can actually look at it as the integral of, well, I'll do the whole thing first. X over the square root of 4 minus x squared plus 2 over the square root of 4 minus x squared. And this is all dx, right? So see, all I did was I broke up that fraction into two parts. Now, this part here looks very similar to that integral that has to do with arcsine. And this one here looks sort of like something we've done previously. Can you figure out which one it is for this? I'll give you a hint. What's the derivative of what's underneath the square root? 2x, right? Or negative 2x, I guess. we have an x up here. So we have something resembling the derivative to this up here. When that's the case, we should know we could basically use u substitution for that and just substitute in for this thing down here. That should give us an answer. So if you want, try to pause the video here, see if you can do this part of the integral by yourself just by using straight up u substitution. When you unpause the video, I'm going to show you what that integral is. Okay, so here we go. I took the integral by making u substitution. U equals the square root of 4 minus x squared. Then in order to find du by dx, I basically implicitly took the derivative of that. I squared both sides to get rid of that ugly square root. And then I implicitly took the derivative. And then I rearranged so that negative u du equals x dx. And then I just substituted in for x dx, negative u du. Simplified, took the integral, and ended up with this as the integral. So the integral of this first term here is just that, negative the square root of 4 minus x squared. Now this second part, I'm also going to simplify that a little bit. I'm going to pull that 2 outside. Oops. I'm going to pull that 2 outside of the integral. And it's going to be 1 over the square root of 4 minus x squared dx. Okay, so which one of the patterns does this look like? The pattern's at the top of the page. Let's just sort of zoom out so we can see it again. It's got just a square root in the denominator. It doesn't have that x out in front. So it clearly looks like this arc sine one, right? So in order for the arc sine one to work, we need to identify what a is, right? Where's my pointer? What a is and what x is, right? And maybe make a substitution if we need to. So zooming back in here, in order to satisfy our pattern, it looks like a is going to be just the square root of this, right? Because it's going to be that squared. Will give us, a squared gives us 4. So that means a has got to be 2, right? And in this case, we don't really need to make a substitution for x because x squared is already there, right? So x is just equal to x. We don't really need to worry about that at all. And once we know that, once we've identified that a equals 2, we can just follow the pattern. So I'm just going to rewrite this first part again, 4 minus x squared. Oh, I actually forgot the plus c for this part because we didn't include a plus c. But anyways, we don't need to include a plus c here because it's just going to be combined plus c between the two integrals. So anyways, 2 times the integral of this, if we're following the pattern, it's just going to be arc sine x over a, in this case a is 2, and that's it, plus c. We only need to include one c because the c from this part and the c from this part will just combine to get one constant value. There we go. That's it. That's our answer. Nothing too crazy as long as we can identify which type of integration to use for each part. How is this one different than the previous ones? Well, if we look over again to our first page and all our patterns, does this one look anything like any of these? Not really, but it's closest to the tan one, to the arctan one, because it doesn't have a square root in the denominator. So is there a way we can sort of make this look like this? This here actually is a specific pattern. It's got a squared plus x squared. Is there a way of turning a quadratic into that? And the answer is yes, and that's called completing the square, hence the title of this section, integrating by completing the square. If you complete the square, you'll end up with something, essentially 2 separate terms that you can then force into looking like this over here. So I'm just going to do it very quickly. I'll link a video on how to complete the square in the description so that if you want, you can check it out on your own time if you need the refresher. So I'm just going to do it super quick here. We essentially factor out the first term, x squared minus 4x, and then plus 7, like that. We factor out the first term. In this case, it's just a is 1, so we don't have to do anything with that. Then what we do is we turn this into a perfect square, and we do that by dividing that b term, the 4, the negative 4, we divide it by 2 and square it. So then we end up with plus 4, and then we can't just add 4 in the middle of the equation. We also have to subtract 4. There we go. And then we can pull the negative 4 out because that's not part of our square, our perfect square trinomial. So we're going to end up with x squared minus 4x plus 4. We pull out that negative 4. Usually we need to multiply by the a term here, but in this case we don't have one. So it's going to be 7 minus 4, which is 3. So plus 3 at the end. And then we realize through our rules of factoring that this is just a perfect square. That is x minus 2 squared plus 3. So we can essentially rewrite this integral with that. I'm going to move the dx off to the side too. So this is going to be x minus 2 squared plus 3 dx. There we go. Now, looking back at our patterns, our pattern for arctan is a squared plus x squared. So in this case, the thing with the x in it comes first. It doesn't matter. We can actually switch those two places. Let's just do that to make it look a little bit closer to that pattern. So it's going to be 1 over 3 plus x minus 2 squared dx. Now it looks really similar to that pattern, right? We have this a term. So in this case, what's a going to be? Because usually a squared would give us that value. So a squared would give us 3. So in this case, that tells us basically, just off to the side, that a has got to be the square root of 3, right? Because if we square it, we're going to get that 3. And I'm going to say u is that other term, x minus 2, that other thing that's squared. So if we do this, we can, again, do our u substitution for this to make it look a little bit prettier for us. Du by dx is just going to equal 1, right? So essentially, du equals dx. So when we make that substitution, it's going to be 1 over, and I'm going to rewrite 3 as root 3 squared plus u squared du, right? Because we can just directly substitute dx for du. Now it looks like our pattern with arctan, right? And we can make the correct substitution. So our pattern for arctan, essentially what it has, it's 1 over a. So a in this case is root 3. So 1 over root 3. And then we follow the rest. Arctan x over a. And in this case, our x or our u is just going to be x minus 2 over root 3 plus c. Right? So this whole thing is in the arctan. I made that substitution for u back. That's really u over root 3. I just did it all in one step. But essentially, that's the answer. There we go. So we turned something that looks rather complicated, a quadratic in the denominator, into something that has arctan in it. You might not think those two things are related, but turns out they are. So we can do this essentially whenever we have a quadratic in the denominator and there's nothing really on top. There's just a 1 on top. We just have a constant. That's when we can use this arctan, the derivative of arctan, or the integral of 1 over 1 plus x squared. Okay. So last question. This one, again, doesn't really match up with 1. If you compare it to your patterns on the previous page, doesn't really match up with 1 that well, but it's closest to the arc sine, right? Because it doesn't have an x in front of that square root. It's got a square root, so it can't be the tan one. And it doesn't have an x in front of there, so it's got to be arc sine. So remember, we're going to try to force it into that arc sine form. And I'm just actually going to write that here on the page. We want it to look like 1 over a squared minus x squared, right? Oh, sorry, the square root of a squared minus x squared. So how can we do that? And the idea is, well, remember, we can turn a quadratic into this by completing the square. So essentially we need to complete the square, right? So in this case, the thing underneath the square root is negative x squared plus 3x. I'm just going to write it in the proper order. That c value is 0. Doesn't matter. It's the same process to complete the square. Factor out the negative 1. Then divide by 2 and square it. So we divide 3 by 2. Oh, let's do the 3x. Divide 3 by 2, so 3 over 2, and square it, which is going to be 9 over 4, right? Plus 9 over 4 minus 9 over 4. And then we pull out that 9 over 4 out of the brackets, minus 3x plus 9 over 4. And that negative 9 over 4 has got to be multiplied by that negative in front. So we end up with plus 9 over 4 here. Okay, now we look at the perfect square. The perfect square is going to be x minus, well, it's that square root of 9 over 4, or whatever that 3 divided by 2 was. So that's going to be 3 over 2 squared plus 9 over 4. So it almost looks like this now, right? The thing with the x we can write second just to make it look more like that. So I just switch the order of them. 9 over 4 minus x minus 3 halves squared. And now the question is, what is the a value and what is the x value? Well, the a value, remember, what squared is going to give us 9 over 4? It's just going to be the square root of 9 over 4, right? So a essentially is going to be the square root of 9 over 4, which is 3 over 2. Because if we square it, we're going to end up with this pattern here. And our u value, I'm going to call it u again, instead of x, we're making a substitution here, is x minus 3 halves. So once again, using our u substitution, I could do du by dx is just equal to 1. Therefore, du is just equal to dx. So that's an easy substitution to make. And let's sort of plug that in here. So this is a definite integral. And again, I'm going to write the dx off to the side, but what we're going to do is we're going to write this as 1 over the square root of, remember the a was 3 over 2, so 3 over 2 squared. And then the x value we substituted for u, minus u squared. And that whole thing, du. So now what we can do is follow our pattern for the arc sine. And the pattern for arc sine tells us it's going to be arc sine x over a. Or in this case, u over a, right? And u we know is just x minus 3 halves over a, which is 3 halves. That's all inside the arc sine. And then just plus c. Oh, sorry, not plus c. This is a definite integral, right? So we have to integrate this between 3 halves and 9 quarters, right? So there we go. Now we might as well finish this off here. We can evaluate arc sine at 9 quarters. And if we do that simplification, basically it's going to simplify, just trust me here or plug it into your calculator. 9 over 4 minus 3 over 2 divided by 3 over 2 should give us 1/2. So arc sine of 1/2. And then minus, if we plug 3 halves in there, it will give us 0. So arc sine 0. Now using your unit circle, you should be able to figure out that arc sine of 1/2, or the inverse sine of 1/2, is pi by 6. And the arc sine of 0 is 0. So pi by 6 is the answer. There we go. So again, be on the lookout for when you have things that look roughly like these three, and you have to take the integral of them, because you can apply these tricks in order to evaluate them.